Okay, so today I'll start on this. We're recalling what we did last time. So in the last class, we were doing essentially ggplot, and so this is a key tool in data visualization. So this is a key tool in data visualization. And I explained over the course of last time how to use this tool. So, for example, you first lay out a coordinate chart by this function right here. So you lay out a coordinate chart. With the appropriate data frame. And once you do that, you set out this idea of placing things layer by layer by a particular geo function. This function could be in many things, right? So we discussed last time. We'll show you examples again today. Just recall, it could be a scatter plot. It could be a line plot. It could be a smooth line. It could be a bar chart. We discussed all these things last time. And then for each of these things, you have to appropriately create a mapping with the aesthetics. And then we discussed what aesthetics were, what mapping were, and what statistics function to use, and how to position the graph. And the last thing we discussed was that you could have many coordinate systems. So one thing we could do is normal Cartesian coordinates, or we could do also polar coordinates like last time. And we also discussed fitting graph. So I'll just quickly go over the examples from last time, and then sort of we can sort of start today's class on linear models in an official way. So the first thing we did last time was a scatter plot, in which I remember I did this. I was this engine size of this empty cars or whatever, and then we said that the engine size was the highway fuel efficiency what you're plotting. If you do a normal scatter plot, you would sort of get all black points. So in this thing, what all have we done? This thing we have done. One is we have layered, we have added a third dimension by taking colors to be from drives, right? From the driving. So there are 4 types of cars: there's 4-wheel drive, front-wheel drive, and rear-wheel drive. And we assign colors to each of them. That's one layer we added on top of the graph. The other thing we have done is we have done this. We try to find if we have to find a particular curve, we found a geom smooth curve, which is what we did. But also we used what's called a filter, right? If you use the filter, and the filter only focused on 4-wheel drives, right? And of course, that tells you how the relationship with the 4-wheel drive looks like. It looks like a curve like this. And if you did one curve for the entire graph, it looks something else. This we did last time. Then I did this thing called a histogram or a bar chart. Here I use this. I use the position command to dodge all the transmissions. So I use the position dodge not together, dodge this DO DG, I guess. And the way and what I was doing was I was just doing, I was trying the various classes of the cars, from the 2-seater, compact, mid-size, and so on, and I'm doing the counts of them. And while doing the counts, I sort of did a count with several across the transmission in the car, like automatic with manual and so on and so forth. So there are so many of the auto L4 here, so many, I think, auto S5 here, there's manual M6 and so on and so forth. This is like a standard bar chart. Then we did this thing in which we flipped the thing. We made it horizontal. That one thing I discussed. And then we also discussed that this is like a very discolors in terms of filling. And the fill was with class, right? The fill was with class. That was the aesthetic we filled out. Finish. So then I also discussed this polar coordinates a little bit, and I said that you could sort of use the same bar chart. You could present polar coordinates. You would just give a circular picture of the graph. This is where we were last time, so in more or less in some sense. So today I'll sort of begin the class in many ways. I'll try and illustrate one particular model that we will analyze in the class in a very sort of strong way, and I'll present it in terms of a data science perspective, not like a statistics perspective first. But before that, so that's the aim of the class. So today we'll begin. So we will introduce a linear model, because I'll explain to you what a linear model is and what it does and so on and so forth. The next thing we will do is we'll understand, let's say, lack of a better word, I'll use the word exploratory. In an exploratory manner, we'll try and understand how it works. So this will set the table for statistical analysis on this space. So we will not do any statistical analysis today. So let me write that down. So no statistical analysis today. Or let's say this week's classes. But what we do is this will give you a good introduction to what linear models are, and in an exploratory way, how to find the correct model. So one particular note I'd like to see is that tell you that all the data sets and codes to be used this week and week 2 code are available now on the website. On this website. So there's a tilde here. I forgot to put the tilde here. Let's put tilde here. So I'll just show you the website on Zoom so you can sort of look at it. This is the course website. So I will fill these things in as I go along. So if you go to my website and go to teaching and go to LSM, it'll give you this entire page. And today I'll use these two data sets, heights and force. I'll explain them as I go along. And I'll use this R code that for today. You can download it. So please download the website. Right, so let me just make a small remark. Make it purple, let's say. So please download the data sets and the R code. So to start before the start of the class. So once you do that, then I can sort of proceed from here and sort of give them. Very cool. So let me just go and show the website again. The website has these. I'll try and populate the website to sort of give you various things about the class and so on and so forth. But as of now, let's just sort of think of the website as sort of just a resource for data sets and R code. And these are not my data sets. I'll do it in a second. So I'll come to where they come from in a second. So let me just show you the RStudio window. So I start with this tool code you will download from the thing. So this is something that you have to decide where the code is. So you can, in mine, it will not be good. So the first thing is that you have to set your working directory. So that's this first thing is that. So let me go back to so while working with the R code, with the R code, make sure you set the correct working directory. Please set the correct working directory. That's very important. If you don't do that, it's a problem. So the working directory, in the sense that what I suggest you do is you place the download thing, so in my case, I have not done this, but in your case, you place both the R code and data set in the same directory. And then I'll show you the how to do in our studio. What you have to do is you have to go to this, you see my tool here at the top. You go to sessions right here, and then you go to set working directory, and then you just place it where the source file location is. That's where it is. In my case, that's not the case, but I've done it. If you want to follow my R code and do it in the way I've done it, then I think what you have to do is, you have to do a little differently than what I've done. You can't. Right. And then you can go and say here, you can go and see here, get WD. If you put this command right here, it'll tell you where the working directory is. And for me, it's right here. That's where all the data sets are. So wherever data sets are, that's where the working directory should be. Very good. So once you've done this, then we can start the class in some sense. So I will now do a description of models, and I'll come and sort of begin the R code that I've discussed in this slide that you'll be using in the classroom. Okay. Very cool. Okay. So let me just come to this slide right now. So here, so what I want to do is I want to understand today's class. So I'll be given a data set. Okay. This is what we're given a data set. Okay. And data set contains typically two variables. So X is an independent variable in the data set, and Y is supposedly dependent. So these are two variables that are in data set. So in some sense, you'll have X is here, you'll have Y is here, then you'll have let's say you have a line like this, and for each value of X, there's a corresponding value of Y, and so on. So let me just write this down as maybe in mathematical fashion, let's say X1, X2, and so on and so forth, and then for each X1, Y1. So there could be measurements of some things or characteristics of something. I mean, it could be various things. And the whole aim or the whole goal, let's say the aim, is, of course, to find the relationship between Y and X. So today we won't do any statistics, so I won't make any assumptions on things. So this is one way of doing it. But today I'll sort of give another redefined goal. So today's goal will be the following. So let me mark it as today. Right. So today's goal. So today's goal will be to provide. So I have a very modest objective. I just want to provide a better low-dimensional summary of my data set. Okay, so that's what I want to do. So let me write this down so that it's clear to you. So, lack of a better word, I'll use the fact that it's a low-dimensional summary of the data set. Okay. So how does one do this? So one should be able to use this to predict X and Y. X for various values of Y, values of X, what is Y? So one should be using this. One should observe. You should be able to observe certain patterns in the data set. Okay, can we observe any patterns? Okay, and then can we use it for prediction? Okay, that means for, let's say, some X for which we don't have, let's say this is X100, let's say, we don't have what Y is. Can I use the orange part to get something about the pink part? Okay, that's one thing I want. So here's a word of caution. So let's write this word of caution maybe in black. Okay, maybe in red itself. So there's sort of a famous saying that this, I don't know if you've seen this saying. It says that all models are wrong and some are useful. But some are useful. So there's sort of a, I don't, there's various versions of this floating around in the world, but this is what I remember in broad terms. So you should treat modeling with a certain pinch of salt. This is a word of caution. I'll begin with an example, and then that will give you a perspective on what I mean by this sentence. So let me go back here. Let me go back. So let's say you're in 12th class and you were doing let's say a chemistry experiment. So you know this standard law, right? This pressure times volume is equal to R times temperature, right? So it's PV equal to RT, right? So this is supposed to be a model for ideal gases, right? But that this is a useful approximation, but no gas satisfies this. Okay, so if you in the existing real world, there's nothing that satisfies the equation. So, but this how does one use this in chemistry and physics? This provides a good approximation. This provides a good approximation to understand the system. That's the aim of the modeling scheme. That's what I meant by this goal right here. See, it's not to sort of give a sort of a description of how the system is behaving. That would be too much to expect. That can never happen with a simple mathematical equation. There's too much going on. And all we want to do is get a good approximation to how the system is behaving. At the same time, today I will not explore the y-axis, just the orange or y-axis. I just think of them as numbers that is given to me, and I know that the relationship is there, and I want to find it. That's broadly what I'm going to do. And always to keep in mind when you do modeling is the following: that a model is not meant to describe reality. That's something people always sort of in the back of the head, that what the expectation is. But the idea is to provide a good approximation to the system. That's what one should observe. One needn't be able to get, the model should not pass through all the points in the data set and so to give you an exact fit. That's what's called overfitting. There are issues with that and various things. So there can be errors in the model, but the errors should be reasonably small, and the model should provide a good approximate system. That's what we should. Okay, that's the goal. So it's not to uncover truth, not to describe reality, but to provide a good approximation. Okay. So now let me go to my go to the R code. So in the R code, if you go top, I have okay. You have to install these two packages. If you have not done that, let me know. But you should do tidyverse and then start the library ggplot, include it, right? Do this. Then let's just start with the first data set. The first data set is called heights.txt. I'll explain what data set is in a second. Then let's just do this ggplot with geom jitter, where I'm sort of splitting the plot. If you get a scatter plot like this, I'll explain what m height is and d height is in a second. So what's happening here is that of the following kind. So this is a scatter plot of. So this is the famous data set by E.S. Pearson in the. Let me go back to my notes. So this is what you're assigned from the code. So this is a data set collected in I think in the 1890s. So this goes back to the era of 1893, I think to 98 in some sense. In the era, this was a person called E.S. Pearson who was collecting, I think collected about 1,500 odd. I think it's 1,375 or 1,500 odd. Heights of mothers and one of the other daughters. Okay, so what the person do? M height was the height of the mother in the family, and they were trying to understand the relationship with the height of the one adult daughter. So it could be any, you don't, not the eldest daughter, one height of one of the adult daughters. Height of one adult daughter in the family. So the only thing was that the age. So one thing they did was they kept the age of this person who was the mother to be less than 65, and the age of the daughter to be at least 80. Okay, that's the data set. Okay, so that's the data set in this file called heights.txt. Go there in this data set called heights.txt. And what have I done? I've just done a scatter plot of it, right? So that's what the thing is. Just look at the R code that we have. All I did was I took the data set, I read it using the read.table command. I called data frame with height.data, and I just use a simple ggplot. So I set the data frame to height data, tested it to be just x and y, m height and d height, and then I just I'll explain what geom jitter is in a second. So what I do this in a second. So I'll come back to it in a second. Let me go to the other one to explain what geom jitter is. So what geom jitter does the following. So the idea is that suppose I did the actual scatter plot, that it all gets smudged into one plot. So the jitter, all it does is it just jitter just adds a small uniform random variable to all the points. So let me just write this down so you're all on the same page, that jitter plot just moves each data point by a small uniform random variable. That's all that jitter plot. That's all the jitter plot is doing. Okay, very good. So now we have this data set of thing, and the question they want to understand was that how does the height variable inherited from mother to the daughter? That's the question. So the question down. So the question down. Question or question in some sense in quotes, or the study, the object of study. Let's say object of study. Following, how does the daughter inherit the height of the mother? So if the mother is tall, the daughter will be tall. The mother is short, the daughter will be tall. So now, if you look at this, right here, this thing, let's look at the first thing that the range seems to be the same, right? For example, like the range of the mother is from 55 to 70 broadly. The range of the daughter is also 55 to 70. That part is kind of clear. The range is the same. So because of this, we can do the same axis for both the height and of course my figure is a little bit rectangular because of the way I plotted it. But if you look at the R code, look at the R guide, the R code, then it's so symmetric. There's no difference. The PDF file, it became sort of needlessly sort of squished because the way the screens are defined. So now what I want to observe is a couple of things. So I've done this jittering to move the point a little bit so you could see all the points, so not all of them are clubbed together because some data are the same thing. And a scatter just plots each x value with each y value. This we know what it does. That's what geom does. Okay. So now, can I just check if is x independent of y? That is, if m height is independent of d height. So that's something you can immediately check. So if they're independent, it'll be all over the place. But somehow you seem to think there's some trend, right? There is some trend. So there is some trend like this. You think that okay, these are all maybe these are all pretty little outliers in the whole thing, but broadly the trend is something like this. That's where the thing is going to go. So let's do one simple thing. Let's go back to that. So now what I can do is I can say, okay, fine. It looks too crowded right now. I'm not able to observe what's going on. Can I just see how the vertical ranges appear? Is the range quite large here? Is the range quite small here? Like suppose the mother is tall, then the daughter is likely to be tall, not short. Is that accurate? If it's here in the middle, can I just see the range is completely like this? So can I observe the ranges in each of the sectors like this? So what I want to do is I want to do a simple thing. I want to just round off everybody to either 58 or 64 or 68, something like that. Let's say. So I want to put 54 somewhere here, 64 somewhere here, and then 68 somewhere. 58, 64, 58, 64, 68. Let's say I want to think of them as clubbed together, and I put them together and see what's going on. So then that's what we did in the next R code. Let's go to the next R code. So next R code, go. So here what we did was we identified everybody in one of the 4 blocks, right? So you're either between 58.5 or 57.5, you're in that range, the mother's height, or you're between 64.5 and if you go here, 63.5, that's not 64, and this is 68, that is 68.5, and then 68, 67.5. Do that. So first you go and identify these people. So that's what the identifying logical variable does. So in your R code, if you do this, you'll get something like this, and then you identify the rows, you get either true or false. So most people are false, some people are true, and then you get them exactly. So once you do this, what you do is you go and grab only those people who satisfy these conditions, who are in this range, either 58, 64, or 68, and then you go plot them. So you do that, now you get a different scatter plot, right? This scatter plot looks different, but it's not elliptically shaped. The axis is not, there's no ellipse here. But the separating these points, you see that these are all well separated. So let me go back to my slide. So let me go back to my plot here. So what do I observe? That by separating these points, I find that people in this range are well separated. They're not colliding. I mean, they do have a range across this y variable, but you don't have very tall mothers with very short daughters. That's not here because there's nobody here. You can clearly see. When you're in the middle, you sort of have a range, and then again, you're very short mothers. You don't have very tall daughters. So in some sense, one can see here that here in this label, you have unusually tall daughters, right? That you can observe, right? And here you have no everybody's within. There are no really short daughters. So these are things that we can immediately observe in the data set. And similarly here, there's no tall. There's no tall. There's no tall. So these are things that we can sort of understand. And one might think, okay, fine. Now somehow this should sort of tell you that maybe these are little outliers you can ignore. These are little outliers you can ignore. So everybody should be like something like this. Is what you could sort of presume in some sense. So you can use this sort of bifurcation of the data to essentially identify outliers. So